right, today we're going to talk about acceleration, and then we're also going to talk about forces. And I think you're going to learn something new about acceleration that you did not know before, so let's go ahead and get started. Acceleration is a change in speed. A lot of times we think acceleration is speeding up, but that's not the official definition. Acceleration is just a change in speed, so that can mean an increase in speed or a decrease in speed. Now, acceleration can also be a change in direction. So you could be going the same speed but change directions, and that would also be acceleration. Now, there's a thing called centripetal acceleration, and this is a circular motion that is uniform, and this is when you move at a constant speed in a circle. So even though your speed is never changing, your direction is always changing, which causes it to be called acceleration. An example of this would be a windmill. Or a merry-go-round. Once it's in its speed that it stays at for a little bit while you're riding, that circular motion, you're going at a constant speed, but you're changing directions. Now, if we want to calculate acceleration, this is the formula. Acceleration equals final velocity minus initial velocity divided by time. And how a lot of times, whenever something is final minus initial, we will use a triangle to represent change. And so the formula for acceleration is acceleration equals the change in velocity divided by time. So that's what that triangle is for. It represents change in velocity. So if you ever see triangle V, that means final velocity minus initial velocity. The SI unit for acceleration is going to be meters per second squared. And that's because you have meters per second on the top divided by seconds, which ends up giving you the meters per second squared. Now, acceleration will be negative when it's slowing down, and acceleration will have a positive number when it's speeding up. Now, before we go to graphing acceleration, what I would like us to do is our practice problems in our notes. So we're going to do the first practice problem together, and then I'm going to let you do 2, 3, and 4 by yourself, and then resume the video so that you can check your answer. Your first question, or your first problem, is a skater goes from a standstill to a speed of 6.7 meters per second in 12 seconds. What is the acceleration of the skater? Now remember, acceleration equals final velocity minus initial velocity. And a lot of times this is how we'll write it, because velocity final, velocity initial, divided by time. Now remember, the final minus initial always equals change in V. So change in V is what you're going to see most of the time because it's just so much easier to write. Now, sometimes we're going to need to find or calculate for time and velocity. And when that happens, we need to use our circle. So now, change in V, or change in velocity, is over time. So you have to put change in velocity on top with time underneath it, and then acceleration goes right down here. Now remember, we write our variables out first, so we have A equals, VF equals, VI equals, and T equals. Now, let's read this again. A skater goes from a standstill to a speed of 6.7 meters per second squared. Now, it says to a speed of 6.7 meters per second squared, so I know that that's my final because it says they go to that speed. So what was my initial velocity? Right here it says that they went from a standstill, so that means 0 meters per second. They were still before they sped up. And they did it in 12 seconds. And then it says, what is the acceleration? So that means we are trying to find acceleration, so it's going to have a question mark. Now, let's write our formula in letters. Remember, you need to do all of these steps because this really helps you not make as many mistakes. And then once you write your equation in letters, you can fill the numbers in. 6.7 meters per second minus 0 meters per second, because that was final minus initial velocity, divided by 12 seconds. Now, let's go ahead and solve this. 6.7 minus 0 is 6.7 meters per second, divided by 12. So you put this in your calculator, and you're going to put 6.7 divided by 12 equals, we'll put down here, acceleration is going to equal 0.59 meters per second squared. Now, I'm going to show you how to double check yourself. Remember that we said acceleration is going to be a positive number if you're increasing speed? So since I have a positive number, let's go back to the problem and make sure that the problem was increasing speed. And it says that a skater goes from a standstill to a speed of 6.7 meters per second. So yes, it's increasing speed, so I should have a positive number, so this should be correct. All right, this is where you're going to pause the tape, do number 2, 3, and 4, and then resume the tape to see the solutions. All right, let's go ahead and look at number 2. As a shuttle bus comes to a normal stop, it slows from 9 meters per second to 0 meters per second in 5 seconds. Find the acceleration of the bus. You have A equals, VF equals, VI equals, and T equals, and we're going to see what we know. Now, immediately at the very end, it says find the acceleration, so that means we don't know what that is. Now, it slows from 9 meters per second to 0 meters per second. If you'll notice, our 0 meters per second is our final velocity because it says it slows from 9 to 0. And our initial velocity is 9 meters per second, and then it gives us the time of 5 seconds. Now, let's go ahead and write our formula in letters. And you always calculate the subtraction first before you divide, but go ahead and fill in your numbers that represent your letters. So VF is 0 meters per second minus VI, which is 9 meters per second, divided by 5 seconds. So let's calculate that. 0 minus 9 is going to be negative 9 meters per second, and then divided by 5 seconds, you would put in your calculator negative 9, divided by 5, and that's going to equal an acceleration of negative 1.8 meters per second squared. Now, this acceleration has a negative number, which means my problem should have been slowing down. And if you look, it says that a bus is coming to a stop, which means it's decreasing speed, so our negative answer would be correct. Let's look at number 3. This is number 3. A car starts from rest and accelerates uniformly over a time of 5.2 seconds for a distance of 100 meters. Determine the acceleration. We have A equals, VF equals, VI equals, and T equals. So we need to see what we have. It says a car starts from rest. If it starts from rest, that means the initial is going to be 0 meters per second and accelerates uniformly over a time of 5.21 seconds. So our time is 5.21 seconds for a distance of 100 meters. Determine the acceleration of the car. Now, this is what you're going to have to do first for this. You have to put speed together with acceleration, all right? Because do you remember that we can do V equals D over T? So I can say a distance of 100 meters divided by 5.21 seconds, right? And so that's going to give me, when you say 100 in your calculator divided by 5.21, it's going to give me a velocity of 19.19 meters per second. And so that's my final velocity, because if I started from rest, and then this gives me my final velocity. So up here I can go put my final velocity of 19.19 meters per second. And it tells me to determine the acceleration. So I know acceleration is question mark. So if you're ever given distance and time and you're missing one of your velocities, make sure that you just go ahead and calculate the distance divided by time to give you that velocity you're missing. Now, acceleration equals VF minus VI over T. And let's go ahead and fill that in with numbers. So 19.19 meters per second minus 0 meters per second divided by 5.21 seconds. And 19.19 minus 0 is 19.19 meters per second divided by 5.21 seconds. And you'll enter that in your calculator as 19.19 divided by 5.21. And so that gives us an acceleration of 3.68 meters per second squared. And our acceleration is positive. Let's look back in our problem. Did the car increase speed? If it did, we've got the right answer. A car starts from rest and accelerates over a time for a distance of 100 meters. Yes, it started from rest and accelerated, which means it was having to increase speed. Now, let's go ahead and go to our final example. A race car traveling at a speed of 46.1 meters per second quickly slows to a speed of 18.5 meters per second in 2.6 seconds. Determine the acceleration. So you have acceleration equals VF equals VI equals and T equals. And it says traveling at a speed of 46.1 quickly slows to a speed of 18.5. So my initial is 46.1 meters per second. My final is 18.5 meters per second. So they didn't stop, they just slowed down. And they did this in 2.6 seconds. Now it says determine the acceleration, so we know that's a question mark. So now let's see, A equals VF minus VI over T. So let's fill in with numbers. Final is 18.5 meters per second minus initial 46.1 meters per second divided by the time of 2.6 seconds. 2.6 seconds. Now the very first thing we have to do is subtract. So in your calculator you're going to say 18.5 minus 46.1, and that's going to equal a negative 27.6 meters per second divided by the 2.6 seconds. And in your calculator, you're going to say negative 27.6 divided by 2.6, and that's going to equal a negative 10.62 meters per second squared acceleration. And now, since it's a negative acceleration, that means we should have been slowing down in our problem, and if you'll look up, you'll notice that we did slow down in our problem. So this should be correct. Now, let's go ahead and move on to our next page of notes so that we can go ahead and finish up Chapter 11. Now let's talk about graphing acceleration. Acceleration can be determined by the slope of a straight line on a velocity versus time graph. And if you'll remember, when we talked about graphing, we said that time was going to be on the x-axis most of the time, and anything else would be on the y. So if you have a velocity versus time graph, that would mean time is plotted on the x-axis, velocity is plotted on the y-axis, and that could be velocity or speed. And when you calculate the slope, if you get a negative slope, that means the object's slowing down. If you get a positive slope, that means the object is speeding up. Now, acceleration can be determined by the slope of a straight line, and that's what we were just talking about. A straight line that does not change means that velocity is not accelerating. So if you've got a straight line on your velocity versus time graph, that means it's not accelerating. However, when velocity changes by the same amount over each time interval, acceleration is constant. So if you have a straight line on a velocity versus time graph, even if it's going up or down, as long as it's straight, that means the acceleration is at a constant rate. If the line is curved, then the acceleration was not constant. It was higher and lower at different times. Now, let's look at fundamental forces. Scientists identify that there are 4 fundamental forces in nature. One is the force of gravity. You have the electromagnetic force that we'll talk about more in depth later on in this semester, the strong nuclear force, and the weak nuclear force. So these are the 4 fundamental forces that we have in nature. Now, these fundamental forces vary in strength. Some are stronger than others. And you also have some forces that act through contact, and other forces act at a distance. Now, pushes and pulls are examples of contact forces. If I push someone or pull someone, that means I'm in contact with them, and that's a contact force. Field forces, however, do not require the objects to touch each other. For example, gravity. If I'm holding a pen in my hand and I let it go, the floor does not come up and grab the pen and pull it down. The force of gravity is acting on that pen at a distance, and it pulls that pen down to the floor. Now let's talk about balanced and unbalanced forces. Whenever there is a net force acting on an object, the object accelerates in the direction of the force. So if I am pushing a desk, the desk is going to accelerate in the direction that I'm pushing. Balanced forces, however, do not change motion. So if there is someone that has the exact same strength as I do, and I'm pushing on one side of the desk, they're pushing on the other, and our forces are balancing each other out, the desk is not going to move. Unbalanced forces do not cancel completely. Another way to think about this is tug of war. If you have a team that's stronger on one side of the tug of war rope, that means you have unbalanced forces. They're not going to cancel completely, and the rope is going to move in the direction of the stronger force. Now, force of friction. This is also a force that takes place on a daily basis. And friction is always opposing motion. Friction is trying to stop motion from happening. And there are two types of friction. There's a static friction, which is the friction between surfaces that are stationary. Like if, for instance, if I have a box on the floor and I want to push that box, but it's at rest and it's not moving, then there is static friction trying to keep that box from moving. So I'm going to have to overcome that static friction to be able to move the box. An example is the pushing the box at rest that I just talked about. Now, kinetic friction is the friction between moving surfaces. So that's two things that are already moving, and they're causing friction while they move. And an example of this would be your brakes in your car. The brakes are trying to stop your tires or your wheels from turning. And so the brakes are trying to press against the wheels, and the wheels are moving, and it's causing friction, which actually causes the car to slow down. So that would be kinetic friction. Now, friction is necessary for many everyday tasks to work correctly. But sometimes you have too much friction and you want it to be lowered. An example of that would be motor oil. Your engine is made up of all different kind of metal parts, and if you do not put motor oil in it, those metal parts rub against one another, they grind against one another, and it causes wear and tear much quicker than if you lubricate your engine with motor oil. Another thing would be a squeaky door hinge. Squeaky door hinge is unwanted friction. That's why it's making that noise. But if you put an oil or a lubricant on that door hinge, it helps it move easier, and you've lowered the unwanted friction. Now, helpful friction is needed sometimes, and it can actually be increased. An example would be batting gloves. When you're playing baseball or softball, when you're holding the bat, your hands can sometimes be slippery and slip off the bat. So sometimes you want to add friction, and that's when you use batting gloves, because the batting gloves help create more friction between your hands and the bat so that you can grip it tighter. That's the same principle for also football gloves. When they're wearing football gloves, they want to be able to catch that football, and they want to add friction by adding the gloves to their hands so the ball doesn't slip out of their hand. All right, and so that's the end of today's video. I would like you to summarize, and this is what I'd like you to summarize. I want you to do a tweet summary. So in 140 characters or less, I would like you to write what you've learned in this video. I hope you have a good evening, and I'll see you in class.